Yo, 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 yo. Hey guys. So this is part 1 of module 2, 2.1 integer exponents. So we are going to learn properties of exponents to make it so that we can add, subtract, multiply, and divide numbers that have exponents really, really easily, especially without a calculator. Now, these are all the properties, and yes, these are the definitions. You can get these definitions down. I know it's a little bit of writing, but we got to get them down. And then also what you're going to do is I'm going to add some examples to these to show you what they mean. So like product of powers means we have the same base and we're multiplying them. So here's what an example of product of powers would be. So if I have a number that's like 4 to the 7th power times 4 to the 9th power. So these are really large numbers because what this is 4 times itself 7 different times. 4 to the 9th power is 4 times itself 9 different times. So a shortcut, instead of us figuring out what 4 times 4 times 4 times 4 times 4 and do a bunch of multiplication, that's going to be a huge number, we can simplify this and keep it in exponential form. The way we do that is we do 4 to the power of 7 plus 9. Because that's what this says. Product of powers means we have the same base, we add the exponents, and we keep the base. So I'm multiplying two numbers with exponents that have the same base. So I'm going to add those exponents because I'm multiplying 4 by itself 7 times, multiplying 4 by itself 9 times. So really I'm multiplying 4 by itself 16 times. And I just leave it like that because I don't expect you guys to figure this out, and we're not using calculators. So 4 to the 7th times 4 to the 9th is 4 to the 16th. That would be an example of product of powers. Quotient of powers is when we're dividing numbers. That's why quotient means divide. So that would be something like if I had 4 to the 9th divided by 4 to the 7th power. So instead of multiplying them, now I'm dividing. That's why we have quotient. Well, here it says subtract the exponents, keep the base. So when we divide, this is really 4 to the 9th minus 7, which is 4 squared. So this is an example of how to use the property. If you don't understand it fully, we're going to look at a lot more examples on the next slide. Power of a power. So this is when I have an exponent, 4 to the 7th, and I'm raising it to another power. So it's when I have something in parentheses with an exponent, and that exponent is being raised to another power. So I have 4 to the 7th all raised to the power of 9. So that means I have 4 to the 7th 9 different times. I have a power being raised to another power. This is where we multiply those exponents. So that'd be 7 times 9, which is 63. That's a huge number. I don't even know how large that number would be, but it's massive. Okay, and then product of a power is if I had something like 4 plus 7 all raised to the power of 9, then what this means is that all of this is raised to the power of 9, so this is really the same thing as 4 to the 9th plus 7 to the 9th. Negative power. So a negative power, this one can be a little bit confusing. If I have 4 to the negative 7, because again, this is just an example of this. What we do is we flip it. So that becomes 1 over, oh, I don't know what happened there. That was weird. I don't like that long line. Let's get rid of it. That makes it 1 over 4 to the 7th, and now it becomes a positive power. So that's why it says we take the reciprocal. We just flip it around. This is 4 over 1, so I move it to the denominator, and then the power becomes positive. And then anything raised to the power of 1, of 0 is 1. So 0 exponent, if I have 4 to the 0 power, that's 1. 5 to the 0 power, that's 1. 8 to the power of 0, all of it's equal to 1. So these are examples. We're going to go over what I'm talking about here right now. So these are problems where you're going to have to simplify these. Okay, so you're going to have to simplify these. And when you do, most of the time, especially if it's a larger exponent, we just leave it in exponential form. Just leave it in exponential form, keep it simple. So what we're going to do is we're going to show you why this is the product of powers, I believe. Yeah, product of powers. Oh, I had to double check. Why this is called the product of powers, how this works, why it works, and then we're going to go from there. So what we're going to do is, if I want to know what 5 squared times 5 to the 5th is, I'm telling you guys we get to leave it in exponential form. I don't want you doing a bunch of multiplication. So if I think about it, 5 to the power of 2, this really is 5 times 5. Okay, so what I did is 5 to the power of 2 is 5 times 5. And I am multiplying that by 5 to the power of 5. Well, 5 to the power of 5 is really, if I expand that out, that's 5 times itself, 5 times. 2, 3, 4, 5. So 5 to the power of 2 times 5 to the power of 5. So what I did is I expanded these out to show what 5 squared really looks like. It's really just 5 times 5. 5 to the 5th power is a shorter and quicker way of writing 5 times 5 times 5 times 5 times 5. Well, if I look here, all of this is being multiplied. So I have 1, 2, 3, 4, 5, 6, 7 5s that are all being multiplied by themselves. So really what I have is 5 to the 7th power. And when I multiply this, I'm done because I don't have to do anything else, because I don't want you to have to multiply 5 to the 7th power. I don't want you to tell me what 5 times 5 times 5 times 5 times 5 times 5. I don't want you to do that. Now, the faster way of doing this is kind of showing that product of powers that we have on the key terms. Because I know this is being multiplied, and I have 5 squared times 5 to the 5th, I really can just add the exponents. So 2 plus 5 is 7. So this is a shortcut. This is the expanded way to show how you get here. You only need to do this. You don't have to do all of this. This is showing you why 5 squared times 5 to the 5th is really 5 to the 7th. Now, same thing for the second one here. So I have 6 to the 8th over 6 to the 3rd. Well, if I were to expand that out, 6 to the 8th, I'll expand over here. That's 6 times 6 times 6, 4, 5, 6, 7. That's 1, 2, 3, yeah, 7, 8. So that's 6 to the 8th. I just wrote out 6 to the 8th power because that's 6 times itself 8 times. And then on the bottom, in the denominator, 6 times 6 times 6. That's 6 to the 3rd power. Well, what happens is whenever you have a number divided by itself, that equals 1, and they cancel out. So all of these cancels. Well, what am I left with? I'm left with 5 6s on the top. So my answer is 6 to the 5th power. So what I did is I expanded 6 to the 8th, I expanded 6 to the 3rd, and I'm left with 6 to the 5th. Because when they cancel out, I have 5 left over. The other way of doing this would have been doing 8 minus 3, the top minus the bottom. And that's the shortcut. 8 minus 3 is 5. Because whenever we're dividing, we just subtract the exponents. So 8 minus 3 is 5. I'm done. There's nothing else I have to do. This one right here, let's look at this one. I have an example over here saying that we just multiply. So 7 squared, all raised to the power 4. What that means is I have this 7 squared 4 times, because this means you just multiply this by itself. Any exponent means you're multiplying it by itself that many times. So 7 squared, I'm going to have to erase this just so I have some space here. 7 squared, I have 7 squared, but I have 4 of those because it's being raised to the 4th power. So I'm expanding this out, again, just to show you why. You don't have to do all of this, but this is to show you why, because it kind of helps us understand these rules. So 7 squared raised to the 4th power, like I said, multiplying to the 4th, anything raised to the 4th power means I have that being multiplied by itself 4 times. So I'm multiplying 7 squared by itself 4 times. Well, 7 squared is really 7 times 7. So again, if I expand that out 4 times, I have 1, 2, 3, 4, 5, 6, 7, 8 sevens. So that's 7 to the 8th power being multiplied. And again, our rule that we just wrote down on the first page in key terms is 7, any power raised to another power, you just multiply those. That's just 7. That's just to the raised to the power of 2 times 4. Well, 2 times 4 is 8. And I'm done. Okay, next one. I'll do a different color for this one. So for this one, for 6 raised to the power of negative 2, that's the negative exponent property. Negative exponents, we just don't like having negative exponents. They're not very friendly. So what we do with negative exponents is we want to make them positive, but the way we do is we have to bring it to we have to flip it or find the reciprocal. So whenever we have a whole number, we can always put it over 1. 6 over 1 is still 6. So if we have a negative exponent, we have to move it from the numerator down to the denominator. And so then we'll move it down, and then we'll put a 1 on the top so there's nothing else up there. So 6 to the negative 2 really becomes 1 over 6 to the positive 2. Once we move it to the bottom, it now becomes positive. And that's an acceptable answer. 1 over 6 squared, I actually should know what 6 squared is. That's 6 times 6. That's 36. So that's just 1 over 36. So 6 to the power of negative 2 is 1 over 36. Okay. Right here, 5 times 6 all raised to the power of 3. So I could do this as 5 to the third times 6 to the third. This is like distributive property. It's like I'm taking this 3 and I'm saying, oh, I got to raise it. That's 5 to the third power, and that's also 6 raised to the power of 3. That'd be 5 to the third times 6 to the third. And then I would just leave it at that. But when you have multiple things inside, just distribute it. Okay. Now I have a fraction raised to the negative power. So what this is saying is I have 2/3 all raised to the power of negative 3. Well, that negative means I got to flip it. So it's going to become 3 over 2 raised to the power of 3. Because I flipped it, and now it becomes positive. So it's like what we did here. We flipped it, and then it became positive. Same thing here. We're going to flip the fraction and make all of it, make the exponent positive. So the negative means we just flip it, make it positive. Okay. And then finally, you will have to do this with variables. With variables, it doesn't change anything. So if I have b to the 4th times b to the 7th times b, well, anytime we have a number that just doesn't have an exponent on it, we can there's a 1 up there. That's a really, really bad 1. I'm sorry. Let me fix that. Not that my handwriting is ever that good, but that's still a bad 1. Ay, ay, ay. Maybe I just can't do it. Sorry, guys. But that's a 1. So anytime we have a letter without an exponent, it's really the same thing as having it to the power of 1. So, like up here, I did 5 squared times 5 to the 5th. We just added the exponent. So this is the same base, b to the 4th times b to the 7th. So that's b to the 4 plus 7 plus 1. Because that's just how many total b's do I have being multiplied here? Well, I have 4 here, I have 7 here, I have 1 here. Well, that's b to the 12th. And I'm done. I can't do anything else, but this is a lot easier way of writing this big thing right here. Okay. So for additional practice, I don't want to go over all of them just for the sake of time, or maybe we will, we'll see. But actually, yeah, let's go over all of them. So for this first one here, because now I have fractions and there's multiple things happening. So this is when we start combining all the properties that we have. So when I have this 9 here as this coefficient, 9 times a to the power of 13. The 9 is nothing's really happening with the 9. There's no number in the denominator that I can simplify it with. There's nothing else being multiplied up here. There's nothing to do. So the 9's just going to move over. But if I look, I do have, I'm off today. I do have this a to the 13 over a to the 3rd. That is very similar to this. That is a quotient of powers. So that's just a to the 13 minus 3, which is a to the 10th. And I just keep the 9. The denominator's gone because everything in the denominator canceled out. And I'm done. So my final answer is just 9 times a to the 10th. So I did a to the 13th over a to the 3rd just on its own to get a to the 10th. And I just kept the 9 with it because there's nothing else I can do with it. For the second one here, if I look, I have 15 over negative 3. Well, if I were looking at just 15 over negative 3, 15 divided by 3 is 5. Positive divided by negative is a negative 5. So I've done my work with the 15 and the negative 3. Because we can actually do that division and simplify that fraction if it was on its own. Now if I look, I just have this k to the 7th over k to the 5th times x to the 3rd. There's a lot going on here, I get it, and it looks a little confusing at first. But if I look here, k to the 7th times x to the 3rd, they don't have the same base. One's a k, one's an x. So I can't say that this is 10 k's because that doesn't make any sense. So I can't actually do anything with this x to the 3rd because there's no other x's here to combine it with or subtract it from or anything. But I can do k to the 7th over k to the 5th. Just like 13 over 3 we subtracted, I can do 7 minus 5 is 2. And then I still have this x to the 3rd. So my final answer is I did 15 divided by negative 3, which is negative 5. K to the 7th divided by k to the 5th is k squared. And the x third stays the same. And the same thing happens when you're multiplying. This is multiplication, right? Well, so I can do 6 times negative 3, which is negative 18. And then I can do x squared times x to the 5th. And that's when I don't actually multiply the exponents. That's when, if I think about it, I have 2 x's over here. I have 5 x's over here. How many x's do I have total? 1, 2, 3, 4, 5, 6, 7. That's x to the 7th. And I'm done. Confusing, there's a lot going on here. Okay, there is a lot, and we're going to get a lot of practice this week. The biggest thing, whoa, sorry guys. Hold on. Hold everything. Everything's weird. Sorry about that. We're back. Fixed it. So here's the biggest thing. Biggest thing you need to have for this is those key terms are super important with the examples next to it to show what it's saying. If you did the expanded form in your notes, that's great because that kind of shows you why it is what it is. And then it's just going to take a lot of practice. Okay. Independent practice, I want you just to try it. If you don't know, just try it. Okay, this is very similar to what we did. You're going to do the division, 14 over 2, m and m. I'm sorry, m to the 15th over m to the 9th. Just do that separately and then do the ends separately. And then this one, see how you do, we can distribute that to everything. Okay, and that's it. I hope this video helped. If you guys have any questions, please let me know. Gordias out.